What if some of the biggest gains in training language models come not from bigger models, but from smarter math beneath the surface? In today's episode, we dive into 3 papers that rethink how optimization really works: correcting hidden bias in modern preconditioned optimizers, adapting learning rates layer by layer using heavy-tailed signals, and reimagining SGD itself beyond the classic Brownian-motion picture. Together, they reveal a fascinating theme. The dynamics of learning may be far more subtle and more powerful than we thought. Let's explore the first paper, correcting stochastic update bias in preconditioned language model optimizers. This paper shows that stochastic preconditioned language model optimizers such as Adam W, Sophia G, and Shampoo are biased estimators of the ideal population update because the gradient and preconditioner are usually computed from the same mini-batch, and because matrix or scalar inversion is nonlinear. The authors separate these effects into gradient preconditioner coupling bias and inverse preconditioner bias, then correct both with a single batch framework. Crossfitting estimates the numerator, gradient, and denominator preconditioner from independent microbatch groups, and a delta method variance correction subtracts the leading inverse bias using microbatch variability. For Adam W and Sophia, the correction is applied element-wise to diagonal preconditioners. For Shampoo, it is applied in the eigenspace of the averaged matrix preconditioner on Quen 2, 5 to 0. 5b, pre-training over 256 K-packed FineWeb EDU sequences. The corrected optimizers reduce held-out cross-entropy by 0.1489 nats for Adam W using a leave one out plus Jensen variant, 0.0701 nats for Sophia G, and 0.1103 nats for Shampoo. In a mixed quality pre-training setup with 20% span replace training sequences, Adam W still improves by 0.0191 nats on clean held out data despite higher training loss, suggesting reduced overfitting to corrupted spans. Instruction tuning on 32K alpaca style examples is mostly neutral, with small gains for retuned Adam W and near ties for Sophia and Shampoo. The main novelty is not a new optimizer geometry, but a statistical bias correction layer that makes existing preconditioned updates closer to their population target. Let's explore the second paper. One LR doesn't fit all heavy tail, guided layer-wise learning rates for LLMs. One LR doesn't fit all argues that a single global learning rate is a poor match for transformer heterogeneity in LLM pre-training and introduces layer-wise learning rate, or LLR, which uses heavy-tailed self-regularization theory to measure each layer's empirical spectral density, fit a power law, and compute a PL alpha Hill exponent as a proxy for how heavy-tailed and well-trained that layer already is. The rule is simple but novel. Layers with lower PL, alpha, Hill, such as attention projections like ATTQ and ATTK, receive smaller learning rates, while layers with higher PL, alpha, Hill, especially FFN and embedding blocks, receive larger ones. Llama embeddings are pinned to the upper LR bound, and LR changes are applied with a soft switch schedule during only the first 20% of training to avoid spikes and reduce overhead. On FineWeb pre-training, LLR improves validation perplexity over tuned uniform Adam W from 21.94 to 20.3 on LLAMA 60M, 17.86 to 17.03 on 135M, 12,9, say 2, 12,7 on Trecentochin Quantum, and 9.77 to 9.59 on 1B, while also outperforming Lars, Lamb, and the sharpness-based baseline. On LLLAMA, 1B, zero-shot common sense accuracy across Pika, Sika, HellaSwag, Winogrand, ArcC, ArcE, and OBQA rises from 47.09% to 49.02%. The method transfers to GPT Nano, Roberta-based fine-tuning, and Muon optimization, and the authors report up to 1.5 times faster convergence with substantially lower tuning overhead than prior layer-wise schemes. Let's explore the third paper, why SGD is not Brownian-motion, a new perspective on stochastic dynamics. This paper argues that stochastic gradient descent should not be modeled as Brownian-motion with Gaussian forcing at finite learning rates. Starting from the exact discrete SGD update with sampling with replacement, the authors derive a master equation and a second-order discrete Fokker-Planck expansion showing that standard Langevin approximations miss terms of order eta squared, including a correction proportional to the squared mean gradient. In a one-dimensional quadratic toy model, This mismatch changes the long-time behavior. The exact discrete dynamics can predict variance growth, where the Langevin model predicts a stationary distribution, so the error is qualitative, not just numerical. Near critical points, the theory diagonalizes the covariance dynamics in the mean Hessian eigenbasis and separates SGD into two regimes: sharp positive curvature directions confine parameter fluctuations to finite variance, while nearly flat directions remain non-stationary and diffuse, with variance growing roughly linearly in time. Empirically, the paper validates these claims on an MLP with 386 parameters on MNIST, a simplified GPT-style model on Shakespeare, and a 6M parameter nano-GPT trained on Wikitext. 2. In the nano-GPT experiment, the discrete theory matches the observed variance plateaus across the top 20 Hessian eigendirections, while the standard Langevin prediction underestimates the plateau by about 23% at learning rate 0.01. The central novelty is the reinterpretation of SGD as deterministic motion in a fluctuating loss landscape, not a particle driven by external Brownian noise. That's a wrap on today's AI paper highlights. Thanks for watching.